All right. Looks like I've got homework 3B here from you. There's the problem set that you should solve for homework 3C. It'll be due on Tuesday the 1st, so a week from today. Looks like a number of people have already submitted water gems calculations for the lab number 4. If you need some more time to do that, just have it submitted by lab today. Remember that we're switching back to Group A at 2 p.m. and Group B at 3. So any announcement questions? Ooh, I'd have to check the schedule. Anybody have the schedule that I handed out to you on the first day of class? It is after chapter, we finished chapter 3, so lecture 17. Here we are, lecture 9. So, oh, is that the 3-day calendar? Yeah. Let me find that out, and I'll let you know in lab today. I've got it indicated on a schedule in my office, but I don't remember. We won't. No, I'll have office hours, and if you have questions as you review, I'll be happy to answer them for you, but we'll cover new content right until the day of the exam. I will tell you this, we'll do the exam during the lab time, though. So we'll have a lab demo that we'll do during the class time on the exam day, and we'll actually take the exam at the 2 o'clock hour so that you have additional time to work it. Okay, well, we're going to talk about hydrostatic forces, continuing with another example on curved surfaces. And so we want to find the forces required to open this curved gate. And what you can see is, based on the shape of it, it's a little bit different than the curved gate that we worked last time, because the water is on the other side. So calculating the area moment of inertia for the curve that does have water on it is going to be a little bit more tricky, but we'll be able to figure it out. All right. If this gate is 4 meters wide, that means that into the page the dimension is 4 meters, and you can see that it has a radius of curvature of 3 meters, so down here to A, all the way to the top. And so when we're working forces on curved gates, what you need to think about is what is going to be the vertical projection of the curved surface. And so in this case, the vertical projection will look like a rectangle that's 3 meters tall and 4 meters wide. That will be the vertical projection. And so we break it up into vertical forces and horizontal forces. The vertical forces are equal to the weight of the water that's above the gate, and the horizontal forces are equal to the hydrostatic forces acting on the vertical projection. And we've already talked about the vertical projection. So, okay, same diagram. Now, let's just analyze and break down the geometry to find out the vertical forces to begin with. If you break the geometry of this, you know, it's 3 meters from edge to edge, and then 2 meters from the water surface to the hinge at B. If we represented that by these two components, component A and component B, and we're going to subtract out of B the part that doesn't have water. And the reason why we're going through this is to find out where is the location of the force. I mean, we can just sort of by estimation come up with a little bit of an idea of the location of the weight of the water. Because remember what we did last time was we said let's divide it up into pieces, and here would be a piece, and so this rectangle is going to have the location of the force will be at the centroid. But where is the location of this force going to be? Probably somewhere around here would be the center of area, if you consider a little bit is to the right, a little bit is to the left. But we need to be able to calculate exactly the location of where is that force located, because the water is going to be pushing down on the gate at different locations, and the moment distance is going to have an impact on the force required F to lift that gate up and open it. So we need to find out how far from the hinge B is that force located. And the process that we're going to go through is we're going to break it up into pieces.
Can you get the 2 meters there?
Uh-huh.
Stretching out 3 meters wide. Because when you put the mark on the back board, put it between the 2 and the B.
2 meters is referring to the distance vertically from B to the water
Yeah,
surface.
I'm talking about with your force center. Put it halfway between, wouldn't it be further between the F and the B?
It would be at 1.5 meters from B, because from the edge to A is 3 meters, so it would be in the middle. Okay, so as it's shown here, it's 1.5 meters from the edge to where the center of area is in that rectangle that's above the hinge. Now we can break element B into 2 pieces. There's the part that has water and the part that doesn't have water. What we learned in the previous lecture is the location of the centroid for this kind of a shape, for the quarter circle, is 4r divided by 3 pi. And so we can find the location of the centroid for element C by subtracting the centroid at element D. And so the way that we're going to do that is we're going to say that element B is a 3 by 3 area. So the area of element B is 3 meters by 3 meters, so that's 9 square meters. Element D has an area of pi r squared divided by 4. So that's pi 3 meters squared divided by 4. That is 7.0686 meters squared. Element C is simply going to be D minus, it's B minus D. B minus D. So I don't know the formula for what's the area of a shape like that. All I'm going to say is I know that it's the leftover area of B, which was a rectangle, minus the area of D. So it's the components of B. These 2 pieces, C plus D equals B. So I'm going to be using that. So the leftover 1.9314 meters squared. Okay, so that tells me the area of it. Now I can find the volume, the force at C, so the vertical force due to the water above the gate within element C is simply going to be the volume of element C multiplied by the unit weight of water. So the volume is going to be 1.9314 meters squared times the distance into the page. It's 4 meters is the distance of that gate, and the unit weight of water, 9810 newtons per meter cubed. And so the force is 75,788 newtons. That's the force of the water acting down. We don't have the location of it yet. Likewise, we can find the force due to element A pretty easily. The force due to element A is simply going to be the volume of element A multiplied by the unit weight of water. And element A is a box that's 2 meters by 3 meters by 4 meters. And the unit weight is 9810 newtons per meter cubed. So the force due to element A is 235,440 newtons. Now, by inspection, we can tell that it's located at 1.5 meters from the edge, from B. So it's 1.5 meters from here to the location of where that force is centered. The location of where this is centered, we're going to have to find by saying that B overall, think about B is at 1.5. And we know that D is at 4r divided by 3 pi. And so the location, this location is the average of that and that. So it is the result of two pieces. B is D and C together. And the way that we combine them together is with a weighted average. And so I'm going to find the location of the force. Location of force at C. Okay, the way that I can do that is I can say that 9 meters squared, which was the location of B overall, and it was at 1.5 meters. So this is overall B is equal to 7.0686 meters squared, which was the area of element D, and then its location is 4r divided by 3 pi. And so I'm putting in the formula for its distance from the edge to the center of area. And if I do that calculation, that works out to 1.27324 meters. And then add 1.9314 meters squared times the unknown distance x, CP of C. So it's an area weighted average. We know that the location of the force at B is in the middle, and it's partly influenced by where this is and partly influenced by where C is. And so obviously element D has the larger area, so it should count more than element C does. This is a way of averaging based on the relative area of each shape. And when we put everything together, we'll be able to calculate that the XCP, as I'm calling it, the XCP, the distance to the center of pressure for element C, the horizontal distance to the center of pressure, 13.5 minus 9 divided by 1.9314. The distance is 2.33 meters. So it makes sense that it's going to be further over to the left than 1.5. So the center of pressure for this, it's 2.33 meters. All the way over would be 3 meters. So it is 2.33 meters from one edge to the other. All right, so these are the vertical forces that we're talking about. This is the location of force C. Here's the magnitude and location of force A. So those are the vertical forces. Next, we want to find what are the horizontal forces that are acting on the projection of the curved surface. So horizontal forces acting on the projection of the curved surface. And I guess I should say on the vertical projection. The vertical projection of the curved surface.
This location of force, that's 9 meters squared times 1.5 meters. What's that supposed to be?
It's an areal weighted average. So 9 square meters is the overall area of element B. And the location of the force for this overall area is 1.5. So that's area times location. And I'm saying that the overall element is equal to the components. And so 7.07 was the area of D, and this is the location of where the force is at D. And this is the area of C, but we had an unknown location. And so that the area average is what allows us to find the location of the force at C. Okay, so the vertical projection looks like a plate that is 4 meters wide and 3 meters tall. That's what the vertical projection looks like. And so we need to know, first of all, the delta H. So the centroid for this is at the center. So vertically speaking, what is the depth from the water surface to the center of the projection? If the projection has a height of 3 meters, then it's going to be 2 meters down to the edge and then another 1.5 meters to the centroid. So delta H is 3.5 meters. Does anybody remember what the definition of Y bar is? In words, what do we call Y bar? Okay. Distance from what to what? From the centroid to the water surface. But that's the same as this, though. Well, how does delta H and Y bar differ? Just like in terms of the word definition.
Y bar follows the orientation of the plate.
Okay, right. So it's the inclined plate orientation distance from surface to centroid. Whereas delta H is just the vertical distance from surface to centroid. So in this case, our projection is vertically oriented, and therefore delta H and Y bar will be the same. Delta H equals Y bar equals 3.5 meters because the projection is vertically oriented. Does anybody have questions about what I mean by projection? Because that's a critical thing to grasp, is the idea of a projection. The projected surface here is a rectangle, even though the gate itself is curved. The vertical projection is a rectangle. All right, so what we can now do is find the area moment of inertia. Remember, that's AB cubed divided by 12. A is the horizontal measurement of 4 meters. B is the vertical measurement of 3 meters cubed divided by 12. The area moment of inertia for this gate is 9 meters to the 4th. We can find the force magnitude will be the pressure at the centroid times the area. So the pressure at the centroid is delta H times gamma. Multiply that by the area of the plate, and that can tell us the magnitude of the force. It's 3.5 meters through the unit weight of water, and multiply by that area of the projection, which is 12 square meters. That is 4 meters by 3 meters. We're talking about the area of the vertical projection. And that gives us that the magnitude of the force is 412,020 newtons. Now the location of the force, anybody have the formula for YCP memorized yet? YCP equals Y bar plus I. Good. That's exactly right. So we had that the Y bar is 3.5 meters plus the area moment of inertia, 9 meters to the 4th, divided by 3.5 meters times the area of 12 meters. Okay, that works out to 3.7143 meters. We can do a moment analysis now, and we can say what forces are acting where and how much force is required to open the gate. So let me draw the gate here, or do my best. All right, so F, trying to open the gate, is this direction, F open. And now we've got the force that we called the force of A. Here's the force of A, which was that rectangle above the gate. We've got over here the force due to element C, as we called it, pushing the gate closed. And then we also had this horizontal force that we just calculated. We'll call that the F sub H, the horizontal force. And all three of these is trying to push the gate closed or turn the gate counterclockwise. Whereas when we want to start opening the gate, we're going to have it to rotate clockwise. So the moment analysis that we can do for that is that we have a force opening, and what moment distance is it for the opening? What's the relevant length parameter that we should use from the hinge to the opening force? 3 meters, good. And now we just use the magnitude of the force and the distance from the hinge at B for all the rest of these. We had 235,440 newtons, and that was at a distance of 1.5 meters, plus 75,788 newtons at a distance of 2.33 meters. And finally, there was the 412,020 newtons acting at a distance of 1.7143 meters. Now, where did I get this 1.7143? If we found that this YCP was 3.7, why am I using 1.7 as the moment distance? So it's the horizontal forces that are pushing on the gate. What do we use as the distance, the moment distance between B and the location of that force? Yeah, right. The YCP is all the way from the water surface to the location of the force. And so if the moment distance is to the hinge, we need to subtract 2 meters. And so it was 3.7143 from water surface to location of the force. And it's 2 meters from water surface to B. And that's why the moment distance here is 1.7143 meters. Okay, so combining all these. Now, I do my calculations in steps wherever I can just to make it easier to double check my work. I went to a school where all of our exams were in a testing center, and we had unlimited time for most of them. So you just go take a test anytime you wanted. You know, there'd be a 2 or 3 day period that the exam was available, and you'd go to the testing center and you'd sit down at your leisure and just take all afternoon if you wanted to work through the exam. And so what I did was I triple checked every calculation. And I had the luxury of time that, for the most part, you here at Marshall don't have that same luxury, and I'm sorry that you don't get that same luxury that I had, but where you can, it still pays to double check your work, and one way to make it easy to do that is breaking your work up into intermediate calculations so that it can be combined easily. So the opening force is 412 kilonewtons. when you add all these together and then divide by 3, which is the moment distance that F has from the hinge. So that's the force required to just barely begin to open it up. We'd have to have a force just slightly greater than that in order to begin rotating it. Well, if the water started rushing out of the gate and the water level decreases, then yeah, it could become considerably easier, depending on how big that is. If it's the entire ocean and the water level is never going to change, then you may need to hold that force a little bit longer. But you'd be, as you begin to lift it, the depth would decrease, so it would get a little easier, yeah. Even if the water level stays the same, at least the position of the gate is changing. All right, so this is the process that we went through, is that we recognized the area B, which was this entire rectangle, was made up of components. And so we found the area of C by subtracting the area D from area B, and likewise found the center of pressure for C with an area weighted average. All right. I don't know why this photo's crooked. They could have just as easily taken it with the camera not crooked. But Cassie, just talk me through what we're seeing here. Be a detective. What kind of an establishment is pictured? That is a gas station, right. So based on that being a gas station, how would you interpret the photo? Like, has anybody here watched Dexter, that show on Showtime? Like, he walks into a room, he's a blood spatter analyst. He can walk into a room and just by looking at like where the blood is, he's got like some whole story of what happened during the murder scene. So based on this photo, give me some big whole story of what happened. Sometimes, not always. Yeah. It's easy to know when you did it, right? Cassie, did you do this? You're going to have to give us the background information. Yeah. Okay. All right. So that would be a reasonable guess. What if I told you though that actually there was no gas in that tank? All right. So the water table may have something to do with it and floated it up. And this is actually a problem not just with gas stations, but it can happen with the people's septic tanks as well. That when you have a tank that here's a couple of different photos. Let me just get the lights again. Here are a couple of photos that show it from other angles. That certainly gasoline can cause a tank to expand, because it's highly volatile. But in this case, what happened was that the gas levels got very low, so that the weight of the tank plus the fluid inside the tank was less than the buoyant force of the water table causing the tank to float. If that doesn't make sense at first, don't worry, it will. We're going to look at buoyancy from a couple of different angles today. But this is actually a pretty common phenomena. I think that these photos come from someplace in Charleston. I'm not sure exactly where that is, but a few students over the years have told me that they recognize the neighborhood and know where it is. But it's related to the principles of buoyancy. So let's watch a little video that's also related to buoyancy. Maybe we'll get lucky and Windows Media Player will work. It all happens pretty quickly.
Oh, those are Maui seconds. Oh, there he is. Shoo! Oh. Red October.
All right, so submarine surfacing. Let me rewind it. We'll watch it again. So why is the submarine?
Oh, there he is. Shoo!
Why did it suddenly come up from underneath the ocean? That's in Hawaii, by the way. Okay, very good. So what you know, maybe just information that you already had, is that a submarine controls its buoyancy by having extra water on board. The submarine, if we had a cross section of the submarine, since there's a void inside of the submarine, this is the passenger compartment here on the inside, they've got some extra water in there, and so that they can control the overall buoyancy of the submarine as a whole by increasing or decreasing the amount of water that's inside there, by pumping it out. So the formula that has to do with buoyancy relates to the fact that the pressure on the bottom of any submerged object is greater than the pressure on the top. Remember that pressure acts equally in all directions, but pressure is greater the deeper down that you go. So you can see that this representation is showing that the pressure forces that are pushing up on the bottom of the object are greater than the pressure forces that are pushing down, simply because the depth is greater. The bottom of the object is submerged deeper than the other one. So we can take a look at the volume of the object itself. We can call it the buoyant volume or the water or the volume displaced. This object, as it's submerged, is pushing water out of the way. Water should be inside of this. If this object, whatever it is, if it's rock or if it's plastic, regardless of the density of the material itself is displacing water. There's water above it, and we can calculate the weight of the water above it, and we can also calculate the buoyant forces that are beneath the object. So if we consider the forces, the relevant forces here, there's forces pushing the object up, and that includes, if you integrate all of the forces on the underside of that object, it's equal to the unit weight of the water multiplied by the volume above the object plus the volume of the object. So volume of A and the volume of object B. The buoyant force acting down, not the buoyant force, the force acting down, so what's trying to push down on the object is simply the weight of the water. So the unit weight multiplied by the volume above the object. And so the buoyant force is the difference between the two. So how do you know if an object is going to float or if it's going to sink? Like if this was rock, you'd know that it would sink, and if it's a very light plastic, it's going to float. And so what's the difference between the two? Okay, the density of the object. And so what's the threshold of whether something will float or whether it will sink? It's what? The density of water, right. So if it's less dense than water, it will float. If it's more dense, then it will sink. Now, that we're talking about in equilibrium, and so it's possible that temporarily something that has a density less than water could be submerged, and this might be plastic, but if it's plastic, it's going to float, and then it's going to come into equilibrium. So initially, it could be submerged, or a dense object can be floating temporarily. Let's do some calculations just to take a look at this. What I'd like you to do is consider a plastic cube that has a volume of 1 meter by 1 meter by 1 meter. So, 1 cubic meter, and its depth under the surface is 3 meters. So calculate the forces on the top of the object, on the bottom of the object, and then the difference between the two. And then compare that to the buoyant force just based on the unit weight of water that's displaced, the unit weight of the liquid that's displaced, which is water, multiplied by the volume of the object itself. While you're doing that, I'm going to hand back some graded items. So if we look at the top area, it is 1 square meter. Depth to top force on the top is pressure times area. So 3 meters times 9810 newtons per meter cubed gives us the pressure at the top, and the area is 1 square meter. So the force is 29,430 newtons. Force on the bottom So the forces that are acting on the top of the cube are pushing the cube down. And you can find the magnitude of the force simply by finding the pressure at that depth and multiplying it by the area of the cubed face that's receiving that top force. So the depth at 3 meters multiplied by 9810, the unit weight of water, and the 1 square meter area gives us that the force pushing on the top of the cube is 29.43 kilonewtons. The force on the bottom is greater because the bottom of the cube is at a larger depth, so it's at 4 meters. From that, we multiply it by the unit weight in the area, get 39,240 newtons, and that's pushing up. So the difference between the two is there's a net force acting upward of 9810 newtons. So it's not coincidental. You know, we're very familiar with 9810. It's because the area was equal to 1 square meter on both the top and the bottom. So that's one way of finding the buoyant force. So this is the force that's pushing upward, is 9810. So will it float? Will it sink? It depends on what the weight of that object is. If that object weighs less than 9810, it's going to rise to the surface and float. If that object weighs more than 9810 newtons, then it's going to sink. The other way to calculate the buoyant force, we know that the buoyant force, F sub B, is equal to the unit weight times the volume displaced. And so how much water did that object push out of the way by its being underwater? It displaced 1 cubic meter of water. So the unit weight of water is 9810 newtons per cubic meter. That box itself has a volume of 1 cubic meter. And so 9810 newtons is the buoyant force. So that's just a little proof that illustrates that buoyant force is equal to the difference between the force on the bottom of the object and the force on the top of the object. We can't do this approach very often because most of the shapes we use are either irregular or complicated enough that it just doesn't make sense for us to try and integrate the forces on the top and the forces on the bottom and find the difference. Far more often, we're going to use the volume displaced approach. We'll either be given the volume of some submerged object or we can calculate it based on different pieces, and then we don't have to keep track of the pressure at different depths. We can just find out what's the volume of it and therefore how much water did it displace. And the buoyant force is equal to the weight of the water that has been displaced. Now there's some tricks to that. Sometimes the water is being displaced from the bottom rather than from the top, and I'll show you an illustration of that just in a minute. But before we move on, are there any questions from this illustration? If an object is only partially submerged, then the buoyant force depends on the fraction of the object that's below the water surface. You've got a homework problem that uses this principle, and the number one mistake from the homework problem that I see is that occasionally students will calculate the buoyant force based on the entire volume. So here, if you said the volume, the buoyant force was equal to the volume A, B, C, D, meaning the volume of the entire object, you'd get the wrong buoyant force. The buoyant force only depends on how much of the object is underneath the surface. So if you think about an iceberg, for example, when you see an iceberg, it's only what's above the water surface is about 1/7 of the total overall volume of the iceberg. So what's underneath the surface is much larger than what's above it, because that's related to the density of ice. All right, here's an example I'd like you to work through and illustrate something kind of interesting in the end as we work through these 5 different steps. But this is a block of plastic, and it's an enormous block of plastic. It's 5 meters tall, so 5 meters is the dimension from the bottom edge to the top edge, 5 meters, and then it's 10 meters wide and 10 meters into the page. And it's floating in the water such that the water level from the bottom edge to the water surface is 4.6 meters, meaning that 0.4 meters of the plastic block is above the water surface. So based on that, calculate the buoyant force. Now, you could calculate the buoyant force as equal to the pressure at the bottom multiplied by the area of the bottom, or you can calculate it by it's the volume of water displaced. Now, the weight of the block and the rest of the questions you have to sort of deduce or figure out on your own. I think all the information is given that once you find the buoyant forces, then everything else you should be able to find relatively easily. So I'll turn you loose to work on that. Feel free to discuss it with a partner, of course. I think that's a great thing to do. And let's see if you can calculate the specific gravity of the block ultimately. The first step of finding the buoyant force is to find the volume of water that's displaced. In other words, what's the volume of the block underneath the water surface? So that is 10 meters by 10 meters by 4.6 meters. Underneath the water surface is 460 cubic meters. So the buoyant force is equal to the weight of the water that's been displaced by the block. So that's 460 cubic meters multiplied by the unit weight of water gives 4.51 meganewtons. So 4.51 times 10 to the 6th newtons. The weight of the block is equal to the buoyant force. Now, understanding that is just to recognize that this block is in equilibrium. It's floating at the surface, and the buoyant force is equal to the weight of the block, and so when it's in equilibrium, that means that the buoyant force and the weight of the block are equal. So just the fact that it's floating in equilibrium tells us we can find that the weight of the block is 4.51 meganewtons. The block volume is simply 5 meters by 10 by 10, so 500 cubic meters. Now, the idea that's asked for in part 4 is the specific weight of the block. The specific weight or the unit weight can be a property that's calculated not only for a liquid. You can calculate the specific weight of a solid, and that's what we're doing here in this example. The volume of the block is known, the weight of the block is known, and so we simply rearrange the formula for unit weight, which is the weight of some object divided by its volume, the volume occupied by a certain amount of weight, and we can find that the unit weight of this block is 9025 newtons per cubic meter. So the specific gravity is just the ratio of the block unit weight and the water unit weight. So 0.92 is the specific gravity, and that explains why it's floating, because its specific gravity is less than 1. Anything that has a specific gravity of less than 1 will, when it's in equilibrium, float. But what's interesting is how this compares to this percent submergence. what percent submerged is this block? We know that 460 cubic meters out of 500 cubic meters are submerged. And so if you divide 460 by 500, you'll find that's 0.92. In other words, it's 92% submerged. And what that tells us is that you can find the unit weight of an object by simply knowing what percent submerged it is. It's related to the specific gravity is the ratio of the unit weight of some object to the unit weight of water. And so if something is 50% submerged as it floats at the surface, then that tells you that its specific gravity is 0.5. Yes?
Is that formula number 4 always true?
Yes.
Okay.
Yeah.
It equals volume times specific.
Yep, that's right. Think of it as if you had a certain amount of water. You know, if you had 3 cubic meters of water, the weight of the water would be the volume of it multiplied by the unit weight. So that formula is always true. Are there,
You do it in different liquids, bigger, because oil, like a specific point, because, or I've been saying like stuff that doesn't float.
yeah. It would be harder to make sense of what we've just been talking about for a liquid than a solid, because you know, the liquid doesn't perch itself on top of the free surface of the water. So you can't tell from a liquid, you know, you can't tell just by the fact that if you had, let's say, water and oil, you wouldn't be able to interpret anything about the specific gravity of the oil in the same way that you can for a solid, because it's going to be whatever distance it is regardless of what its specific weight is. As long as its specific weight is less than 1, it'll float on top of the water.
Well, like, instead of floating something on water, float on mercury. Get it to some point that
Mm.
a piece of iron's gonna sink, or what, you know.
You could put the liquid into a container, a very light container. You know, if you had the liquid into plastic or a styrofoam container, and then it would be, you know, in one spot, and how it floats would give you a sense of its unit weight that way.
Would this work, this percentage work, if you were using it to liquid with water, not if we were floating plastic in
Yeah, well, then we'd need to just make note of the fact that we'd have to have 2 different specific gravities. There would be the block versus water, and then there would be the whatever liquid you're using versus water. So you'd have to do 2 conversions. But you could do the same kind of calculation. But I mean, as you point out, mercury is so dense that in this case, if it had been mercury, then it wouldn't be so deeply submerged. It would be sitting up much higher in the water if the liquid was mercury, because for however much this block weighs, it wouldn't need to displace as much water. In fact, it would need to displace 13.6 times less of the water. And so instead of displacing, you know, we know that its weight will stay the same, and the volume and the weight of liquid being displaced will be the same. But instead of displacing 460 cubic meters, if it was mercury, then the volume displaced would have been 460 cubic meters divided by 13.56. So, have you got a calculator handy? How much is that? 34. So it would only need to displace 34 cubic meters. And so 34 out of 500, that's less than 10%. And so if it was this plastic box sitting in mercury, in a pool of mercury, it would look more like, here's the mercury, there's the plastic, and then it would be riding very high in the liquid. In the lab today, we're dealing with buoyancy. You're going to be doing 2 different things. You're going to be measuring how deeply submerged a plastic box is. It's actually like a little boat. You're going to find out how deeply submerged it is with a known weight. And then what you're going to do is you're going to put an unknown weight into this little boat, and you're going to see how deeply it's sitting. It's kind of like a barge. You're going to take a look at how deeply it's sitting in the water in order to estimate what the weight of the unknown object is. And in fact, that's what they do with ships. Sometimes ships that, transatlantic, trans-Pacific shipping where they're moving grain from country to country, or iron ore, when they move ore from Australia to China, the way that they estimate how much ore has been moved from place to place, they don't take the ship out of the water and put it on a scale somewhere. They can't do that. But they have the ship markings on the side of the boat, and they can see how deeply submerged it is in the water, and they take temperature measurements to find out what's the density of the water, and the way that they actually estimate the weight of the cargo that's been moved from place to place is by how much water's been displaced. So this concept's very relevant. Think about this scenario where we've got an irregularly shaped gate keeping an orifice, water from coming out of an orifice. So we've got an irregular shape here. Now, the way that you'd find the force required to hold this plate steady would be the direct way. You'd find out what's the pressure at every point. You'd break it up into lots of little pieces, and you'd find out what's the pressure for this piece, what's the area of it. So the force is pressure times area. The numerical method is to integrate for lots of little elements. It'd be a lower pressure here at the top, it'd be a higher pressure at the bottom, or you can find out the weight, the force required to hold the system steady is just equal to the weight of the water above it. And so it's a buoyant force effect. And so on the left side, it's a little bit more direct. But think about what's happening in this case. Now, in this case, on the diagram on the right-hand side, you've got some irregularly shaped gate that's plugging a hole. If that gate is removed, then water's going to come shooting out of that hole. But the way that you find out the force that you have to push down to hold that gate steady, it's equal to the weight of the water that would be above the gate. If you go extend the water surface over towards the left, keep a hypothetical water surface elevation, then the force required to resist that pressure acting over the area of the gate is simply the weight of the water that would be above it if water was above it, which is kind of an unusual concept, but there are some of the homework problems in the book. I don't think I assigned you any where the trick is noticing this thing, that the weight of the water is above it, imaginary weight of the water above it, but it's still an important concept to know. All right, we're going to work one more example today. We may only get partway through it before we need to break, but in this example, what we've got is a wooden block, and that's partially floating, and then a metal object that's fully submerged, and they're connected together by a thin wire. And we know that the wooden block its dimensions are given and its specific gravity is known. And so by knowing its dimensions and specific gravity, we are able to find out what its weight is. So we can calculate the weight of the block. Based on the drawing, we can find the buoyant force. Now look at how much submerged it is. It's submerged 75%. But the specific gravity is 0.3, which means it should, if it was unencumbered by anything else, it would only be submerged 30% because of the specific gravity of the block. So why is it submerged more than 30%? Yeah, it's that metal object that's down beneath that's dragging it down. And so what we can do, that the direction that our analysis is headed in, is we're going to compare the difference between how submerged it should be and how submerged it is. And that extra amount of submergence is because of the weight of that metal object beneath the water surface. And so from that, we're going to be able to find out the weight of that object too, based on the difference in the buoyancy that it ought to be and the buoyancy that it is. And so we want to find the tension in the cable and the mass of the object as our ending points of this example. So let's find the, first of all, the buoyant force that's acting on 1. Okay, the buoyant force acting on 1. Force due to buoyancy is equal to the volume displaced multiplied by the unit weight of water. Now, this is an easy place to make a mistake. We have a unit weight of the block, but the buoyant force is independent of what the block is made out of. The force of the water pushing on the block is unaffected by if the block is made out of wood or plastic or metal. The buoyant force depends on whatever fluid is displaced. In this case, the fluid is water. So when we go through and do the calculations, we first of all have to find the volume that's displaced. The volume is 7.5 millimeters times 50 millimeters times 50 millimeters divided by 10 to the 9th cubic millimeters per cubic meter. That's kind of an awkward thing. It probably would have been better just to convert those to meters to begin with, but there's 10 to the 9th cubic millimeters in a cubic meter. That's the volume displaced. And now multiplying it by the unit weight of the fluid that's displaced. And that fluid is water. So 9810 newtons per cubic meter. The buoyant force for object 1 is 0.184 newtons. That is how much the water is pushing up on 1. All right, what about the buoyant force on 2? Even though we don't yet know what the weight of object 2 is, since we have its volume given, we can find the buoyant force that's acting on that object. And it doesn't even give us any dimensions for the shape. Did you notice that? It doesn't tell us the width of that little metal object. It doesn't tell us the height. None of that matters. Its shape is irrelevant. It's only about the volume. So the buoyant force acting on object 2 is simply the volume of water displaced multiplied by the unit weight of the fluid that's displaced. So we know that the volume is 6,600 cubic millimeters, and we divide by, there's 10 to the 9th cubic millimeters, 10 to the 9th cubic millimeters per cubic meter. So from that we'll get the volume in cubic meters, and we'll multiply it by the unit weight of the fluid. Even though it's made out of metal, it doesn't matter. The buoyant force just depends on the volume of water displaced and the unit weight of water. So that is 0.065 newtons. That is the buoyant force FB2. Okay, the weight of the block weight is the specific gravity that's defined. Sg is 0.3 multiplied by the unit weight of water times the volume of the block. So the specific gravity is 0.3, and that tells us the unit weight of the block relative to the unit weight of water. So that's why we have to multiply it by 9810 newtons per cubic meter, is because when we've multiplied 9810 by 0.3, that gives us the unit weight of the block, and then multiply it by the volume of the block, which was 10 millimeters by 50 millimeters by 50 millimeters divided by 10 to the 9th cubic millimeters per cubic meter. Okay, from that we get that the weight of the block is 0.0736 newtons. So far, we have enough information to do a little force balance. We can say, here is the wooden block. The wooden block has a buoyant force acting up, and it has a weight acting down, and then there's something else as well. There's the tension in the cable pulling it down. So let me draw that a little bit differently. We've got our block. There's the tension in the cable. There's the weight of the block. And then there's buoyant force. Now, don't be alarmed by the fact that I drew the buoyant force off to the side. That's just because I wanted to put the tension in the middle. It's a vertical force balance that we're doing, so it doesn't matter that I've moved that buoyant force off to the side a little bit. So let's look at the force balance. What we've got is the tension is acting down, the weight is acting down, and the buoyant force is acting up. So the buoyant force is up, the weight is down, and the tension is down. And in equilibrium, they're all equal to 0.
That would be 1?
Yes. Yep, this is object 1. We're doing the force balance on object 1. So we can rearrange that to find out that the tension in the cable will be FB1 minus the weight of object 1. So the tension in the cable is 0.184 newtons minus 0.0736 newtons. The tension in the cable is 0.1104 newtons. All right. Likewise, we can do a force balance on the block, and that's where we'll head when we pick up in class next time. We will start the force balance on object 2. Before you go, let's just remind ourselves that lab today is at 2 o'clock for Group A, 3 o'clock for Group B. If you haven't already finished the water gems assignment, that's due in lab. And if you do get a chance, it would be great for you to read over the instructions in the lab handout so you can be familiar with that. And I will see you this afternoon.